The uncomfortable truth about the AI boom. Where are the productivity gains? Opening. The $400 wager. Two of the world's most respected economists have made a wager on the future of the American economy. On one side stands Erik Brynjolfsson, the productivity optimist. He predicts that labor productivity in America's private non-farm business sector will grow by more than 1.8% a year on average between the first quarter of 2020 and the final quarter of 2029. On the other side stands Robert Gordon, the distinguished skeptic from Northwestern University. He believes it will not. The amount at stake is $400 to be donated to charity. For a wager concerning artificial intelligence, the future of work, and perhaps the trajectory of the global economy, the sum is admirably restrained. One might even call it proportionate to the personal consequences for the two participants. The debate itself, however, is anything but modest. Paul Krugman once put the matter rather neatly. Productivity isn't everything, but in the long run, it is almost everything. The line comes from The Age of Diminished Expectations. His point was simple. Over long periods, a society's capacity to improve living standards depends chiefly on how much more output each worker can produce. So if artificial intelligence is genuinely a civilization-altering technology, it must eventually reveal itself not merely in share prices, conference speeches, or increasingly theatrical product demonstrations. It must appear in the numbers, in productivity, in output, and ultimately in living standards. This film examines what the OECD's research tells us about that prospect, and about the rather considerable distance between the promise of AI and the economy in which it must actually operate. Part 1. The literature of numbers. Let us begin with the forecasts. The OECD compares several prominent estimates of how much artificial intelligence might add to annual labor productivity growth over the next decade. The results do not merely differ, they inhabit rather different economic universes. Daron Acemoglu's estimate for the United States is close to 1/10 of a percentage point per year. At the opposite end, one McKinsey scenario reaches as high as 3.4 percentage points. The broader McKinsey range begins at roughly 0.6 and extends to 3.4 percentage points, depending on assumptions about adoption, automation, and the reorganization of work. The difference between Acemoglu's central estimate and McKinsey's upper bound is approximately 34-fold, one technology, one decade, and forecasts separated by nearly the entire history of modern productivity growth. Economic forecasting is often presented as a technical exercise in measurement. At times, it resembles literature written with equations. Every estimate contains a plot. How rapidly will firms adopt the technology? How many tasks can actually be performed more efficiently? Will AI merely assist workers or replace entire bundles of work? Will productivity gains remain concentrated in a few occupations? And will organizations redesign themselves sufficiently to capture the benefits, change the assumptions, and the ending changes with them? The numbers are not meaningless, but they are conditional, and the conditions are doing a great deal of the work. Part 2. The shadow of the 1990s. The grey band running across the OECD chart represents an important historical benchmark. During the American information and communications technology boom of the mid-1990s and early 2000s, computers, software, and the internet contributed to a substantial acceleration in productivity. Depending on the method and period used, the additional annual productivity contribution is commonly placed at roughly 1 to 1.5 percentage points. This gives us a useful scale. At McKinsey's upper bound, AI would produce an effect considerably larger than the productivity acceleration associated with the personal computer and the internet. Under Acemoglu's estimate, by contrast, AI would register as a comparatively modest improvement, economically useful certainly, but rather less than the industrial transformation implied by current valuations. The OECD places its main estimate between these extremes. Its model suggests that AI could add approximately 0.25 to 0.6 percentage points to annual total factor productivity growth over a 10-year horizon. Expressed in terms of labor productivity, that corresponds to roughly 0.4 to 0.9 percentage points per year. This is not trivial, nor is it the economic equivalent of a technological singularity. It is a meaningful productivity gain, surrounded by the sort of qualifications international organizations have spent decades perfecting. The numbers are not meaningless, but they are conditional, and the conditions are doing a great deal of the work. Part 3. From the worker to the economy. How does the OECD arrive at these figures? The underlying logic is quite sensible. First, it considers the productivity improvement that an individual worker may obtain when using AI for a particular task. Experiments have found significant gains in activities such as customer support, business consulting and software development. But a worker does not spend the entire day performing one AI-compatible task. So the second step is to estimate the share of tasks within each occupation and industry that AI can meaningfully affect. The third step is adoption, not whether the technology exists, not whether a chief executive has mentioned it during an earnings call, but whether firms actually integrate it into normal production. These elements are then combined across sectors, with each sector weighted according to its importance in the economy. Input-output relationships are also included, because productivity gains in one industry may reduce costs or raise output elsewhere. The framework is rigorous. The problem lies not in the arithmetic, but in the future. Adoption rates must be assumed, exposure must be estimated, the capability of future models must be projected, and the willingness of organizations to rebuild their processes must be inferred from institutions that still struggle to replace outdated payroll software. The formula may be precise. Its inputs remain human expectations about how quickly other humans will change. Part 4. The G7 Productivity Divide. The OECD extends its model across the G7. The results reveal substantial differences. Under the most optimistic scenario, high adoption and expanded AI capabilities, the estimated increase in annual labor productivity growth is around 1.28 percentage points in the United States and 1.27 percentage points in the United Kingdom. It is, however, 0.89 percentage points in Italy and 0.82 percentage points in Japan. These differences arise partly from adoption. They also reflect economic structure. Countries with larger shares of finance, information technology, consulting, and other knowledge-intensive services are more exposed to the capabilities of generative AI. Economies with greater weight in construction, traditional manufacturing, hospitality, and personal services may benefit less directly. A language model can draft a financial memorandum in seconds. It remains less accomplished at repairing a roof in Manchester during February. This is because countries with a high proportion of knowledge-intensive service industries, such as finance and IT, fully reap the benefits. A more interesting point is the actual adoption rate. Even in the US and Canada, which are considered the most advanced, the rate of integrating AI into core businesses is merely at the 6% level. This means that while everyone talks about the AI revolution every day and the stock market fluctuates, 94% of the actual industrial field is still stuck with existing methods and Excel spreadsheets. Part 5. The Global Productivity Divide. The picture becomes more severe when we move beyond the G7. The OECD's later work on the global productivity divide finds that low-income and lower-middle-income countries face a structural disadvantage. AI's largest immediate gains are expected in knowledge-intensive activities. Yet many poorer economies remain heavily dependent on agriculture, informal employment, routine physical labor, and low-productivity services. The relevant jobs are often less exposed to current generative AI systems, and exposure is only the beginning. Effective adoption requires reliable electricity, affordable broadband, digital payment systems, suitable devices, trained workers, access to finance and institutions capable of managing data and risk. The OECD identifies weak digital infrastructure, limited skills, high adoption costs, and underdeveloped regulatory systems as major barriers. In wealthy economies, the AI debate concerns which model is marginally better at reasoning. In poorer economies, the more immediate question may be whether the office has uninterrupted electricity. There is something faintly surreal about presenting a frontier language model to a firm that lacks stable connectivity, digitized records, or formal access to credit. It is rather like placing an expensive washing machine in the middle of a desert. The engineering may be excellent. The surrounding system remains inconveniently absent. This does not mean poorer countries cannot benefit, but it does mean that access to a chatbot should not be confused with the productive capacity required to transform an economy. Part 6. Youth, India, and the Search for an Exception. The outlook is not entirely bleak. Many lower-income economies have young populations. Younger workers may adapt more readily to new digital tools, acquire new skills more quickly, and enter occupations that did not previously exist. International spillovers may also help. Models developed in advanced economies can be accessed elsewhere without every country bearing the full research cost. India provides the clearest example of a possible alternative pathway. Its large English-speaking workforce, established software sector, and business process services industry give it a stronger platform for deploying AI in internationally traded services. A country need not build the world's leading foundation model to benefit from AI. It may capture value by integrating models into software development, customer operations, finance, design, translation, and professional services. Yet demographics do not replace infrastructure. A young population is an opportunity. It is not a power grid, nor is it a university system, a fiber network, a functioning capital market, or a coherent digital strategy. Youth may make adaptation easier. It does not make complementary investment optional. Part 7. Baumol's rather inconvenient disease. Now we return to the advanced economies. Suppose AI makes programming, legal research, and financial analysis dramatically more efficient. Does that guarantee rapid growth across the whole economy? Not necessarily. This is where economics introduces one of its less glamorous but more durable ideas. Baumol's cost disease. Imagine that AI makes certain legal or software tasks 10 times faster. The price of producing those services may fall, output may rise, but consumers do not necessarily demand 10 times as many contracts, computer programs, or consultancy reports. Meanwhile, other services remain stubbornly labor-intensive. A nursery worker cannot safely care for 10 times as many children simply because an AI system has summarized the safeguarding guidance. A nurse cannot conduct 10 physical examinations simultaneously. A carer cannot compress an hour of human attention into 6 minutes and call it a productivity miracle. As productivity rises rapidly in some sectors, wages tend to rise across the economy. Labor-intensive services must then pay higher wages, even when their own measured productivity has changed very little. Their relative costs increase. Over time, more spending and employment may shift towards sectors in which productivity growth is slow. The OECD estimates that when AI gains are uneven and adjustment is difficult, this Baumol effect can reduce the aggregate productivity benefit by roughly 1/6 relative to a frictionless benchmark. It also notes that similar reallocation effects have historically imposed a persistent drag on economy-wide growth. This is the dry economic response to the claim that AI will transform everything. It may transform many things. The things it transforms least may then account for a larger share of what society pays for. Part 8. The productivity J-curve. There is, however, a reason not to dismiss the optimists. New general-purpose technologies rarely raise measured productivity the moment they arrive. They require complementary investment. Firms must redesign workflows, retrain staff, clean data, build new systems, establish controls, and create products that were previously impossible. During this period, resources are being consumed, but the full benefits have not yet appeared. Measured productivity may remain weak, it may even decline. Only later, once the organizational investment begins to yield returns, does the curve turn upwards. This is the productivity J-curve. Brynjolfsson explicitly cites it in support of his wager. He argues that artificial intelligence, like previous general-purpose technologies, may initially suppress measured productivity whilst firms accumulate intangible assets, new processes, skills, products, and services. The gains arrive later, when those investments are harvested. History provides some support. Robert Solow famously observed in 1987 that the computer age could be seen everywhere except in the productivity statistics. The acceleration arrived later, after firms had reorganized production around computers, networks, and software. The question is whether AI is now approaching a similar turning point. Recent American productivity growth has at times been stronger than the sluggish rates seen during much of the 2000s. But quarterly figures are volatile. They are influenced by the business cycle, changes in hours worked, labor market adjustment, investment, and sectoral composition. A few strong quarters do not establish an AI productivity boom. They merely keep the possibility alive. The J-curve is a plausible hypothesis. It is not a permission slip to declare every missing productivity gain temporarily invisible. At some point, the tail must actually rise. Closing. Inertia or innovation. Artificial intelligence is not a magic wand for economic growth. Its capabilities matter, but so do institutions, infrastructure, and organization. The firms that benefit most will not necessarily be those that purchase the most AI licenses. They will be those prepared to redesign core tasks, change decision-making structures, train workers, and build complementary systems around the technology. Countries without reliable electricity, digital infrastructure, skills, and capital may remain largely outside the productivity boom. And even within advanced economies, rapid gains in selected industries may be diluted by slow-moving, labor-intensive services and by the stubborn arithmetic of Baumol's cost disease. The wager between Erik Brynjolfsson and Robert Gordon will ultimately be settled using official American productivity data after the final quarter of 2029. Will innovation overcome the inertia of existing institutions? Or will AI become another extraordinary technology whose macroeconomic effects prove more modest than its demonstrations? We do not yet know. What we do know is that the bet itself is worth $400. A restrained financial exposure to a question involving trillions of dollars in investment, millions of jobs, and the future path of living standards. Whatever the result, the personal economic shock experienced by either economist is likely to be statistically indistinguishable from zero. Perhaps that is also the proper attitude towards the wider AI debate. Neither panic nor faith, neither dismissal nor worship, just a patient examination of the evidence. Because if AI is truly transforming the economy, eventually it will have to do something rather old-fashioned. It will have to show up in the productivity statistics. Thank you for watching.